Hello, welcome to the Speed Automation Pro Tip video. My name is Charlene Erickson, and today I'm going to be talking about distributed generation or distributed energy resources in feeder automation software. When we start talking about distributed generation, DG, or DER in Blizzard systems, the main issues we encounter deal with loading. That would be load masking and unpredictable load support. Let's talk a little bit more about that. On feeder X, we can see that we've got at least one health problem and a number of zones with expired load. We can look at the logs to see exactly what's going on with the health problems. The first one is that it doesn't know the power direction for at least one phase. RX3 is reporting that it is in the reverse direction, but it would be expected to be in the forward direction. So the calculated power direction is unknown. That is a health problem. And then we've also got a major coherency problem because the downstream device has 75 amps, whereas RX2, the next upstream device, has only 25 amps. This does not make sense to the automation system, and therefore it declares a health problem. And after a while, all of those zone loads then go expired because of that health problem. In order to solve this, we need to map in the DG that is hidden at the end of feeder X. So I'm going to put that back in service so that the feeder automation software knows about it, and that will resolve all of our health problems. Let's talk a little bit more about that load masking and unpredictable load support. The load limit for all of these devices is 1,000. That includes the transformers. That will make it easy for us to do some math. If we look at the instantaneous currents, it would appear based on this loading here, if we lost feeder Z source voltage and needed to pick up all of feeder Z with feeder Y in this transformer, if we just add 400 to 525, it would look like we could pick that up because it's less than 1,000. But that does not take into account the fact that this DER is carrying a portion of load. So let's just run that test and see what happens. Now we'll note that that last zone on feeder Z did not get picked up, but why is that? It looks like it could have. We're still only at 825, but what the feeder automation system does is calculates what the load would be without that DER. So we have a computed cumulative load, and it puts our transformer at the load limit of 1,000, and that takes out the contribution from the DER. Let's restore our voltage and put the system back to normal. Let's take a minute and talk about the requirements that are needed to include DG or DER in our feeder automation software. First thing we're going to need is the directionality of the current flow at every device that could be attached to the DG. We need to know which direction the power is flowing in order to properly calculate the loading. We also need the currents at the DG to know how much load it is carrying. Those currents can be estimated, and I'll show you a couple of options for that. And then another thing we like to have is a block of close at the DG device. And I'll give you an example now of why we use that. In this one line, we have a DER or DG over on feeder Z now. Now what were to happen if we put a fault in this first zone? You'll see that as the feeder automation software goes to isolate and restore, it also sends a block of close to the DG, the DER, so that it does not close back into the fault. And then if we reset everything, for another example, let's lose the voltage on feeder Z again. And again, you'll notice as the feeder automation system reconfigures that it sends a block of close to that DG again. Even though the zone the DG is connected to is energized, it's a different feeder source than its normal feeder source. Then we'll restore the voltage. And if we do a return to normal, there is an option to automatically reconnect that DG. Let's take a minute and talk about how the DG is configured in our feeder automation software. If we look in this Topology editor and we navigate down to the zone level, this is where we're going to find our distributed generation configuration. This is the one we were just looking at, the ERC, and you can see it's controllable. We can set the display color and the nameplate rating. We can also set up what kind of switching device it is, if it's a switch or something else, give it a data concentrator, normal automation controls, and logical current. Because this is a controllable device, we're going to get our currents directly from the device. But what if we have another device that is not controllable? There is no protection device. In that case, we may need to use logical currents. And this is where that would be configured. You can set it on a global level, or you can set it on a device level. By default, all of the logical currents are disabled and we expect actual values to come from a device. But we can also select fixed values, which would use the nameplate rating and always assume that if it is connected, it is outputting the nameplate rating. The other option we have is solar. For a solar device, we need to set the latitude and longitude for the device. Then the automation software will calculate based on sun angle how much load the DG is carrying. So how does it do that? We do have another feature to estimate how much solar output is generated. You do need to have Microsoft Excel installed in order to run this estimation tool. If Microsoft Excel is installed, the output estimation tool can be selected. When we click on it, we'll see that we want to input first a nameplate rating. Let's just choose 300, and then we put in a latitude and longitude. Let's put in the latitude and longitude of our office. And then we can pick a day in which to estimate it. That will open up Microsoft Excel with a nice little graph where you can see what the estimated output for that DG is at any given time of day. You can see our sunrise is about 7 and our sunset is a little after 7 p.m. on September 20th this year. Or we can put in an airport in southern Argentina. We've got about the same amount of daylight as our office, it's just a little bit earlier in the day from the looks of it. And perhaps not as strong of sun this time of year. And that is how you can use the solar estimation tool. I should also mention when calculating the solar output, the feed automation software assumes the solar panel is flat on the ground and there are no clouds in the sky. It does not check the weather. I hope you found this video useful today. Let me know if you have any questions. Thank you for watching.